Hello, this is Professor Kuehn, and welcome back to my lectures on astronomy, where we've been looking at Galileo's Starry Messenger, published in 1610, in which he describes his use of a telescope to discover the moons of Jupiter and the stars that comprise the Milky Way galaxy, and also the mountains and valleys that are on the lunar surface, the surface of our moon. In my last two lectures, we went through the introductory comments, some of the biographical notes on Galileo, and then we also talked about his dedication, his introduction, which was dedicated to this work, Starry Messenger, was dedicated to Cosimo de' Medici, the fourth Grand Duke of Tuscany. We talked about that a little bit in my previous lecture. And we also began into the text itself of the Starry Messenger, which begins on page 230 in A Student's Guide Through the Great Physics Texts, Volume 1. So let's pick up where we left off. We're about the middle of page 231. I'm going to continue reading and make comments as I go. So he says here, about 10 months ago, a report reached my ears that a Dutchman had constructed a spyglass by the aid of which visible objects, although a great distance from the eye of the observer, were seen distinctly as if near, and some demonstrations of its wonderful performances were reported, which some gave credence to, but others contradicted. So in other words, this Dutchman had invented a telescope. A few days later, I received confirmation of the report in a letter written from Paris by a noble Frenchman, Jacques Baudouin. This finally determined me to give myself up first to inquire into the principle of the spyglass, and then to consider the means by which I might arrive at the invention of a similar instrument. After a little while, I succeeded, through deep study of the theory of refraction, that is, how light bends as it is traveling through lenses or other glass materials. I prepared a tube, at first of lead, in the ends of which I fitted two glass lenses, both plane on one side, but on the other side one spherically convex and the other concave. So here he's describing how his telescope was built. So let me make a sketch here to give you a sense of what this might have looked like. He took a piece of lead foil. So imagine a sheet of lead. He probably used lead because it is very easy to bend. So think of aluminum foil, but instead a piece of lead foil. And then he wrapped this up into a tube. So going like this, he wrapped it into a tube like this. You might imagine it looking something like this. And then he put a couple of lenses, one in this side, a glass lens in that side, and a glass lens in this side. And this is a Galilean telescope. To be more precise, he's using a specific lens configuration. So if this is his eye, then he is going to be looking into, he says, a lens that is flat or plane on one side and concave. This is a concave lens. And then this is a cross section, by the way, of the lead foil. So this is the lead foil, and maybe I'll color these lenses with blue to indicate that they're glass. And the other lens was flat on one side and convex. So it looks like this. So this is the kind of telescope that he built, and then he looks at things. And he says, then bringing my eye to the concave lens, I saw objects satisfactorily far and near. So again, this is the concave lens, and this is the convex lens. I said that correctly. Okay. For they appeared 1/3 of the distance and 9 times larger than when they are seen with the natural eye alone. So here he's giving a sense of how much magnification an object exhibits when viewed through this. And I'll draw some pictures and make a few more comments about this in a minute. Let me continue reading. Shortly afterward, I constructed another one, more precise spyglass, which magnified objects more than 60 times. Finally, by sparing neither labor nor expense, I succeeded in constructing for myself an instrument so superior that objects seen through it appear magnified nearly 1,000 times and more than 30 times nearer than if viewed by the natural powers of sight alone. So maybe I'll say a few things about this to talk about how he's arriving at these numbers. So he claims that the magnification of his original telescope is such that, so his original scope made objects appear, he says, 1/3 the distance, like they're 1/3 as far away, or 9 times larger. How does he arrive at these numbers? So 9 times larger or 1/3 the distance. Well, let me make a sketch here to give you a feeling of what's going on. So let's suppose your eye is right here. I'll make your eye look blue. And let's suppose that you are looking at some object. And let's make that object orange. And I'm just going to make a square object to make this drawing a little bit easier. And this square object is going to take up some kind of fraction of your field of view. So I'm going to draw some lines here. I'm going to try to draw some straight lines. One like that, and another one like that, and another one going through that corner, and another one going through kind of the other corner like that. Okay, and let's suppose that this object that you're viewing is some distance d away from you, and it has some area a. You might think the area to be, I don't know, 1 square centimeter. So suppose area is 1 square centimeter. Now, what if you were to ask, how big of an object would you need to have at a distance 2d away from you? So 2d. How big would an object have to be at a distance 2d away from you in order to appear to be the same size as the original object? So if I were to take another object out here, how large would this object have to be so that it takes up the same fraction of your field of view? And if you were to use some geometry, specifically similar triangles, you would find that the object would have to have an area of 4a. So each of these little squares has the same area as this original square. And in other words, what I'm saying, an object of area 4a, or in this case it'd be 4 square centimeters, at a distance 2d looks the same, or looks to be the same size as an object of area A, or 1 square centimeter, at distance d. Okay, so in other words, if you double the distance of an object, you actually need to make that object 4 times as big in order to take up the exact same fraction of your field of view, or for it to appear to be the same size to you. Okay, and now here's the point that I'd like to make here. So conversely, if an object appears to be 4 times the area, or if an object appears to you, that is from your perspective, to be 4 times the area of another object, so if an object appears to you to be 4 times the area of another object, then the object is either actually 4 times as big, actually 4 times as large, or perhaps it might be twice as close. It might be half the distance. Okay, so if you have some object, if you're holding up one object in front of your face and it appears to have a certain size, if something else appears to you have 4 times that size, it might actually be 4 times the size, or it might just be half the distance to your eye that the initial object was. Okay, and that's where Galileo is getting at these numbers. He's saying if an object appears to be 9 times larger, it appears, you could also interpret it as being 1/3 of the distance, okay? And that's what he's saying here in this very first sentence. Now, how did we get to that? Well, if we look at this diagram I drew down here, if the distance instead of 2d was, oops, let me go back for a moment. If the distance was not 1d or 2d, but 3d, 3 times the distance, well, how big would this object have to be? I'll draw another square here, like this. And as it ends up at 3 times the distance, you'd have to have 9 times the area. And that's where he gets these numbers. So each of these has the area of the initial object. Okay. Okay, so that's what he's saying here about the relationship between the apparent size of an object and the apparent distance of an object. And it's giving a sense of what the magnification of his telescope is. So let's jump ahead to the next page. Well, he says at the bottom of page 231, it would be altogether a waste of time to enumerate the number and importance of the benefits with which this instrument may be expected to confer when used by land or by sea. So you can use this telescope to see ships appearing at a great distance, okay? But without paying attention to its use for terrestrial objects, I betook myself to observation of the heavenly bodies. So whereas others were using it for terrestrial viewing, he's going to look at the stars. First of all, I viewed the moon as near as if it were scarcely 2 radii of the Earth distant. So remember, it's normally, the moon is actually located 60 Earth radii distant, and it is going to appear to him to be 2 radii of the Earth distance. In other words, it's 30 times closer. And hence he's going to say it appears 900 times as large, because 30 squared is 900. He says, after the moon, I frequently observed other heavenly bodies, both fixed stars and planets, with incredible delight. And when I saw their very great number, I began to consider about a method by which I might be able to measure their distances apart, and finally I found one. And so there you have it. In the next couple of paragraphs, he's going to describe a little bit more about the theory of his telescope and the relationship between the apparent size and the apparent distance. So I'm going to skip over that for now, jump on to the next page. And in the next page, he's going to talk about some of the specific observations that he makes. So he says now, at the top of page 233, the first full paragraph, now let me review the observations I made during the past 2 months, again calling the attention of all who are eager to true philosophy to the beginnings of great contemplations. So these observations, these scientific observations, these careful observations are going to have philosophical implications. And the first thing that he does is he describes his observations of the surface of the moon. And let me just say a couple of things first, and then we'll stop and go into another lecture. I'll pick this up in more earnest in the next lecture. He says, let me speak first of the surface of the moon that is turned toward us. For the sake of being understood more easily, I distinguish 2 parts in it, which I call respectively the brighter and the darker. The brighter part seems to surround and pervade the whole hemisphere, but the darker part, like a sort of cloud, stains the moon's surface and makes it appear covered with spots. Now these spots, as they are somewhat dark and of considerable size, are plain to everyone, and every age has seen them. So when you look at the moon with your eye, you go out tonight and look at it, certain parts of it appear kind of cloudy and dark, and other parts appear bright. He says, thus I shall call them great or ancient spots, to distinguish them from other spots smaller in size, but so thickly scattered that they sprinkle the whole surface of the moon, especially the brighter portions of it. The latter spots have never been observed by anyone before me. From my observations of them, often repeated, I have been led to the opinion which I have expressed, that is, I feel sure that the surface of the moon is not perfectly smooth, free from inequalities and exactly spherical, as a large school of philosophers holds with regard to the moon and the other heavenly bodies, but that on the contrary, it is full of inequalities, uneven, full of hollows and protuberances, things sticking out, just like the surface of the earth itself, which is varied everywhere by lofty mountains and deep valleys, the appearance from which we may gather this conclusion are the following. So in addition to the general dark regions and bright regions of the moon, if you look at it with a telescope, you see many dark and bright regions that he calls spots, and these betray the existence of valleys and mountains and other features that are very similar to the same kind of features that one observes on the Earth. And what he's going to do in the next few pages is describe in some detail these observations. I'd highly recommend you read through these. It's a fascinating read, and Galileo is quite a good writer.